welcome to this short follow-up video where we discuss the implementation for the stable marriage problem that we discussed in the previous video. Now, as I mentioned there, this problem is available both in the ICPC regional archives as well as the Codechef problem archive, and the code that I'm going to share with you right now is tested on the Codechef platform. So if you want to run it on the ICPC platform instead, just make sure that you have appropriately adjusted it for proper input-output, and just make sure to double check all the details at least once. Okay, so with that said, let's get started. Our code for this problem is going to be in C++, and as usual, to begin with, we have the usual reading of input. Everything here is pretty standard. We want to have 2n vectors to store the 2n rankings that have been given to us, and the rankings are given as space-separated integers, and the men and the women are represented as integers between 1 and n. So everything here is fairly straightforward. The only little annoying detail to keep in mind is that the lines that give you the preferences begin with a number denoting whose preference it is. So the first line is the first woman's preference, and it starts with a 1 and is then followed by n integers between 1 to n in some order, which gives you the actual ranking. So you have to remember to ignore this leading number. If you forget to do that, your algorithm is going to be all messed up. So it's a very tiny detail, but just useful to note. Okay, so that's why you have the standalone cn person outside of the for loop, which just takes this input and doesn't really do anything with it, and then you read the rest of it into a vector. So we have a collection of n vectors for the n woman and a different collection of n vectors for the n men. And you'll notice that I'm also reversing these rankings so that I have the top preferences at the end of the array. This just makes it easy for me to access the top choice that these people have, because that's something that we will need to do frequently. But you can absolutely do this also without reversing the list. It would really be the same thing. It's a matter of minor detail. Okay, so all the heavy lifting is done in this solve function. So let's go and try to understand what's happening in solve. It's going to use a few helper functions whose objectives will be self-explanatory. So I will show you the helper functions at the very end, but I'll show you the main function, the main solve function to begin with. So here what we are going to maintain is a list of engagements in the arrays or the vectors we and me. So we of I is going to store the current partner of the I plus 1th woman, and me of I stores the current partner of the I plus 1th man. And the reason this is off by 1 is because the men and the woman in the problem statement are denoted as numbers between 1 and n, whereas these arrays are of course indexed from 0 to n minus 1. So that's why the offset, but just keep in mind that this is what is happening. Of course, to begin with, if you remember also from the pseudocode, everybody is free. There are no engagements. Nobody is matched to anybody. So we will use -1 to denote that somebody is currently single. So the initialization is clearly that everybody is single to begin with. So that's what is happening here. Now we turn to the main logic of actually creating the matching. So the first thing we said was that as long as there is a single man left who still has to propose to somebody, we are going to go ahead and actually execute that proposal. So we have this helper function which tells us if there are any single people remaining, and you could examine either of the arrays because we and me are symmetric in reflecting the matched state of all the people involved. So we could just pass either of them to the singles remaining helper function, and this helper function will return true if there is at least one person who is still single at this point, and will return false otherwise. So hopefully this while statement makes sense. Now if there is at least one person remaining who is single, we enter the loop, and then we go over the list of all men, and in particular we focus on those men who are currently single. So that is the for loop and the if block here. Now, if we have a man who is single, so if me of I is -1, which is to say that the I plus 1th man is currently single, then we want this man to propose to the woman who is currently at the top of his list. So that just essentially amounts to pulling back the last element of the array, because remember we said that we have reversed the preference list, so the top element is really at the bottom of the array, or it's the last element of the array. So that's what I'm pulling in here, and we have a -1 to adjust for the indexing. So this is the correct index to refer to in the arrays that we are storing, but of course it's what is being stored is the number or the identity of the woman that this person likes the most currently. So we remove this element from mi's vector as well, because we will have no need for it later. Remember that you always go further down in your preference list and you never look back. So this is just all about identifying the person that the I+1th man will propose to now. Now, once we are done with this, we actually try and look at what happens when the proposal is made. So here we have to look at what's going on with the woman that we are now calling top. So for this woman, we have to distinguish between the cases of whether she is currently single or engaged. So let's do the easy case first. If this woman is currently single, then we go ahead and make the match. There's nothing else that needs to be done. The match can be immediately made. On the other hand, if the woman is currently engaged, then we have to compare the person that she's engaged to with the person who is making the proposal. So let's store in the variable competitor the current match of this woman. And now what we have to do is compare the competitor with the man I+1. So we have another helper function getRank, which tells us how the competitor is ranked and how the current man is ranked. Remember, all of these +1s and -1s are just adjusting for the indexing. If you read it carefully, you will see that all of it is consistent. So we use the getRank function to retrieve the ranks of these two candidates in the preference list of the woman who is denoted by the variable top, and we compare these two ranks. Now remember that smaller ranks are going to be better. That's how the helper function is set up. And so if the man I+1 has a lower rank, then that means that the current engagement needs to be broken, and the previous person that top was engaged to, we need to signify that he's back in the singles pool of men. So we make sure to set the competitor's index in the ME array to -1, and we also make sure that man I+1 is matched with top. That is going to happen with this match helper function. So that's essentially the heart of the algorithm. That's all the business that we need to do. We check if the woman who is at the top of the I+1th man's preference list is single or not. If she's single, we make the match immediately. If she's not single, then we compare the new match with the old one, and if the new match is better, then we break off the old engagement and make the new match. Otherwise, we do nothing, and the man who was making the proposal continues to remain single, and we just walk out of the else block without any work being done in that case. So that's the entire algorithm, more or less. The only thing left is to show you how the helper functions work. Now, all of these helper functions are fairly standard. What getRank will do is it will try to return the rank of the person in a given list, and the reason we have a n- here is again because we had reversed the list to begin with. If you did not reverse the list, then you don't need to do this n- calculation here. You can just directly return the location of the person in the list. Now, the way the find function works is that it actually gives you an index in memory, so you need to adjust that to get the actual rank. You could also use something like distance to figure out the rank. So anything works. So you can have your own version of the getRank function depending on which built-in functions you use and whether you reversed the list in the beginning or not. So your version may vary a little bit from what we have here, but just make sure that the way you index things, the way you number things is consistent between all the functions that you write. Now, the singles remaining function is also really simple. It just boils down to identifying if the input array has a -1 or not. So all we are doing here is just checking if there is an occurrence of -1 or not. If there is no occurrence of -1, we return false, or otherwise we return true. Now, the exact conditional in this if statement here is basically based on the documentation for the find function. So if the find function returns an index which is just after the last first location of the array, that's a signal that the thing that you were looking for was not found. So that's what we have here. I'm sure there are many other ways of writing this as well, so take your pick, but essentially the logic that you need to implement is to return false if -1 was not found in the array. So any way you have of doing that should be just fine. Now the match function essentially updates the engagements array to reflect that a particular man got matched with a particular woman. So this again is really simple. You need to go to the wth index in the woman's engagement array and make sure that that is updated to M, and you need to go to the mth index in the men's engagement array and make sure that that's updated to W. Again, you could make a choice here about whether you want to reflect the true identity of the person, or do you want to use the index that you are going to be using, which is going to be essentially the identity -1. Again, whatever you do is fine as long as you're consistent in your code and how you use it. So I've tried to be careful here, and I think everything here is reasonably robust. As usual, you can find the entire code here in the GitHub repository, and if you have any feedback, then that would be absolutely very welcome. Also, if you manage to write this in a different language, please do submit a pull request so that we can add it to the official repository. So with that, we come to the conclusion of the stable marriage problem. I think I should quickly mention that the one thing I haven't shown you on the slides is the output statement. Of course, if you are just working from the video and you try to imitate all of this code, please don't forget to write your final output statement where you output the stable matching that you found. Okay, so with that, I think we are truly done here, and let's call this a wrap. We have one more module left, which is going to be an interesting one because we will not really discuss any more problems, but we will in fact look at problems for which greedy strategies actually fail, and hopefully that will serve as a useful warning for us to keep in mind when we are applying this very powerful but also very slippery sort of paradigm in contest programming. So I'll see you there. Thanks for watching, and bye for now.